everyone. Thanks a lot for being here. My name is Dong Song. I'm a professor at UC Berkeley and also founder and CEO at a company called Oasis Labs. Today, I'll talk about AI and security, challenges, lessons, and future directions. As we all know, that deep learning has been making great advancements. For example, AlphaGo has won over world champion, and deep learning is empowering everyday products. On one hand, we see that the development and adoption of deep learning is growing exponentially. On the other hand, in another landscape, we are seeing a different trend, where in the landscape of security, unfortunately, we are seeing that the attacks are increasing in scale and sophistication. For example, over 400,000 IoT devices have been compromised and used to cause one of the largest distributed network service attacks in history in the attack of Mirai botnet. And we continue to see really large-scale data breaches where attackers compromise companies' infrastructure to steal sensitive information about hundreds of millions of users in a single attack. And also, we continue to see attacks entering new landscape, including the power grid and banking systems. And hence, there are a lot of really important and exciting challenges at the intersection between AI and security. When we talk about the AI and the security, there are two directions. One, how will the rise of AI alter the security landscape? How can AI help security, for example? On the other hand, how will the security or insecurity impact the deployment of AI? It's important to study both of these two directions. And first, let me show you how the rise of AI can help with security. So deep learning has already shown great improvements for security capabilities as well. So for example, face recognition has been widely deployed. And also, research has shown that deep learning can help with improving the capabilities for malware detection, vulnerability detection, and also fraud detection. So here, let me give you one concrete example of some of our recent work showing how deep learning can be used to help improve security in the domain of Internet of Things. The area of Internet of Things is growing exponentially. It's estimated that by year 2020, we are going to see over, it's estimated in the near future, we are going to see over 50 billion IoT devices deployed over the internet. However, a lot of these IoT devices, unfortunately, are plagued with vulnerabilities, in particular because they utilize a lot of third-party codes, such as open-source third-party code. And these IoT devices can contain, essentially, can suffer from vulnerabilities in these third-party codes. And hence, one question is, when a vulnerability is discovered in a piece of third-party code, how can we quickly identify whether a certain IoT device, whether its firmware contains a similar vulnerability? In our recent work, we showed that by using graph embedding, we can develop more effective methods to essentially address this problem. In particular, in our work, when given the firmware and also given the vulnerability function, we can, by using program analysis, we convert these functions into code graphs. And then by using graph embedding and deep neural networks, we can then convert these code graphs actually into these embeddings. And then by computing the similarity between two vectors, we can then tell whether a firmware function is similar to a vulnerable function, and hence detect whether a piece of firmware contains a recently discovered vulnerability in the third-party code. Using this approach, our work shows that we can achieve orders of magnitude improvements in both training time and serving time, and also improve the accuracy for identifying vulnerable firmware. And in our work, we were able to identify vulnerabilities in real-world firmware. So this is just one example showing that using deep learning, in this case graph embedding, it helped us to identify vulnerability, and also in the future we can use machine learning to help patch this vulnerability as well. So now I also want to give you, just very quickly, a couple other examples illustrating how deep learning can help addressing other security problems. One is how we can develop automatic agents for attack detection, analysis, and defense. As we continue to improve the security of software systems, actually one fundamental weakness of these cyber systems is humans. Study has shown that over 80% of attacks actually start with a social engineering attack, such as a phishing email. And even though we have methods to continue to improve the security of software system, but we can't do an upgrade to humans, to human brains. The question is, what can we do to address this problem? In our recent work, we are using and developing NLP techniques for building chatbots, which can observe the communication between a user and a potential attacker. When the chatbot detects a suspicious communication, the chatbot can then try to issue a challenge question to the suspicious sender of the email, for example, and try to detect whether the sender is being impersonating as someone else. So this is one example how we can use new advancements in AI and machine learning to try aim to build automatic agents for attack detection, analysis, and defense. Another example that I want to briefly mention is for automatic verification of software security. Again, we have all learned about the great success of AlphaGo. So in AlphaGo, we use reinforcement learning techniques to train an agent to play Go. So here, we are just training an agent to play Go, to play a game. The question is, can we use the advancement of AI and machine learning to train other types of agents that help us solve other, even more important problems? So for example, in order to improve the security and correctness of software, one important domain of techniques is called program verification. Essentially, for example, using theorem proving and other formal verification techniques to try to prove that a piece of code satisfies certain security properties. But however, in general, these programming verification techniques are, in particular theorem proving techniques, they are very labor intensive and requires a lot of manual work. The question is, can we utilize the recent advancements in AI and machine learning and deep learning to help us to automate this process, to help us train automated agents that can help us prove theorems. So in our recent work called GamePads, we developed a learning environment and with initial steps towards this goal. And the GamePad is also open source. So, so far, I've shown you one example how the improvement of AI capabilities can enable new security capabilities. On the other hand, security is also very important for AI. In particular, security can enable better AI. When we talk about machine learning, when we deploy machine learning, we need to consider machine learning in the presence of attackers for a number of reasons. So first, it's important to consider, so first, history has shown that attackers always follow the footsteps of new technology development, or sometimes even leads it. And also this time, the stake is even higher with AI. As AI controls more and more systems, attackers will have higher and higher incentives to compromise them. And as AI becomes more and more capable, the consequence of misuse by attacker will become more and more severe. So when we consider machine learning in the presence of attackers, we need to consider several different aspects. So first, we need to consider how attackers may attack AI. Attackers can attack AI for several different types of aspects. First, attacker can try to attack the integrity of AI by causing the learning system to not produce intended or correct results, or even causing the learning system to produce targeted outcome that's designed by the attacker. The attacker can also try to attack the confidentiality of the learning system to try to learn sensitive information about individuals. To address these problems, we need better security in the learning systems. Another aspect is that attackers can also try to misuse AI. For example, attackers can try to misuse AI to attack other systems, for example, to find vulnerabilities in other systems, to devise new attacks, and so on. In order to address these issues, we need better security in other systems. So first, let's look at how attackers may attack AI. And the first aspect, how attackers may attack the integrity of the learning system. To motivate that, to see why that's important, first let's consider the scenario of self-driving cars. With self-driving cars, as the autonomous vehicle is driving around the environment, it needs to observe the environment, for example, to recognize traffic signs, such as stop signs and so on, in order to make correct decisions. So here are some images of traffic signs. And the second one is an image of a real-world stop sign in Berkeley. And as you can see on the traffic sign, there are some stickers and man-made marks. But however, today's computer vision system, powered by deep learning, actually works pretty well and can give correct classification for these images. But however, what if attackers actually try to maliciously manipulate these images, these traffic signs, and try to add certain specific perturbations that are specifically crafted to try to fool the computer vision system? And we call these results adversarial examples. So these are images with adversarial perturbations added to them to specifically designed to try to fool the vision system. For example, in this case, these images actually cause the computer vision system to misclassify, and in this case, to misclassify the stop sign into speed limit sign. So these are perturbations added to the digital image. One question is, can these adversarial examples also exist in the physical world? And moreover, can these adversarial examples in the physical world also remain effective under different viewing conditions and different distances and other viewing conditions? So in our recent work, we set out to explore this question. And what we have shown is that, unfortunately, the answer is yes. That the adversarial examples do exist in the physical world, where we can physically manipulate actual physical objects in the real world. And this physical adversarial example can fool a computer vision system to make wrong classification even under different viewing distances and angles and so on. So the images here are images showing this, this result. And to further illustrate the point, here let me show you a video. And in this video, what you will see is it has two frames. two frames side by side. And once I start playing the video, you'll see the car is going to drive towards the end of the road. And at the end of the road, there's a traffic sign, a stop sign. And at the bottom of each frame, you will see the prediction label given by the image classification system. And in these two frames, in one frame, the image was the original image. The traffic sign was the original traffic sign without any modification. And in the other frame, the traffic sign was adversarially manipulated to fool the computer vision system. So I leave it as a quiz. You can tell me after you see the video to tell me which frame contains the stop sign that has been adversarially manipulated. So now let me just play the video. It's taking some time to play. Hold on, let me try again. Usually it just plays. I don't know whether it's just slow, it's playing, but okay, let me try it once more. If it doesn't play, then maybe I can just explain what you would have seen in the video. Oops. Okay, yeah, I don't know why it's not playing. But OK, so let me just explain to you what you would have seen is that actually, with the video, the car is driving towards the traffic sign. And for the frame that contains the traffic sign that has not been manipulated, the computer vision system gives the correct classification the whole way, which is a stop sign. But in the other frame, the prediction from the computer vision system throughout the whole driving process, it gives mostly the wrong answer. Gives the speed limit sign 45 miles per hour. And this is an example demonstrating that adversary examples can be effective in the physical world and also can remain effective under different viewing distances, angles, and so on. So that's just one example illustrating why it's important to ensure integrity of the learning system. As you can see, with these type of attacks, it can have severe consequences as we deploy the AI and machine learning system broadly. So unfortunately, adversary examples are prevalent in deep learning systems. It's not just in image classification. It's also prevalent in other types of tasks and in other types of deep learning systems, including generative models, deep reinforcement learning, and other tasks such as visual Q&A. And also, adversary examples can also be effective under different threat models, which I will explain in a second. So just to illustrate the point further, let me give you a little bit, just a couple other examples. So one is in the domain of visual question and answer, VQA. So the problem of VQA is that you are given two inputs. One is the image, and one is a text question. For example, in this case, what is the woman feeding the giraffe? When you feed these two, for example, to the machine learning system, in this case, to the VQA system, it will give you an answer. And in this case, it gives the correct answer, carrot. So the question is, do these VQE systems also suffer from adversarial example phenomenon? So here we studied state-of-the-art VQA systems, actually developed also at Berkeley. And here are some example results. So here's one question where it's a plane. And here it shows the benign image. And when we feed the benign image and the question to the trained VQA model, it gives the right answer wrong way. The question here is that can we actually develop an adversarial perturbation of the benign image such that when we feed this adversarial example to the VQA model, it will fool the VQA model to give the wrong answer, in particular to give the wrong answer sky. So in this case, this is an adversarial example generated from our attack. As you can see, with human eyes, the adversarial example looks very similar to the benign image. But however, when we feed this adversarial example to the VQA model, it gives the wrong answer, the targeted answer, sky. Also similarly, here's a question, how many cats are there? And when we feed the benign image to the VQA model, it gives the right answer, 1. But however, here we show that when we generate this adversarial example, again, to human eyes, you can see that this adversarial example looks almost identical to the original image. But however, when we feed this adversarial example to the VQA model, it gives the wrong answer 2. So it shows that there are 2 cats in the image. And similarly, we studied the phenomena of whether adversarial examples can fool deep reinforcement learning agents as well. Again, AlphaGo was trained using deep reinforcement learning, and deep reinforcement learning has been a very popular and effective method for training automatic agents. So in our work here, we also explored whether adversarial examples can fool these deep reinforcement learning trained agents. So in the frame on the left-hand side, that's the trained agent. As you can see, that the trained agent actually, the agent has been trained very well, and here it's winning the game, almost getting, getting all the scores. And okay, so this video plays. So in the middle frame, this is the same agent, but we added the adversarial perturbation to the video frame. And as you can see, even though it's the same agent and also to human eyes, you can't differentiate between the left side frame and the middle frame. But here, this agent has been completely fooled. The agent is behaving incorrectly and actually gets a minimum score. So this is also an example showing that for deep reinforcement learning trained agents, also it's very easy to fool the agents. And so far, the work that I have mentioned, they are all in the category of what we call white box attacks. So with these white box attacks, we assume that the attackers knows the details of the victim model, knows the architecture, and knows the parameters. And hence, the attacker can craft very effective adversarial examples to fool the machine learning model. However, in our study, and also in other researchers' study, we have shown that a much weaker threat model, black box attacks, can also be very efficient. Can also be very effective. In this case, attacker can successfully launch these adversarial example attacks to the machine learning model, even when the attacker actually does not know the details of the model, doesn't know the architecture of the model, and doesn't know the parameter of the model. And we have developed different types of black box attacks to demonstrate this. So overall, what I have shown you is just the tip of the iceberg. Is in the general domain of what we call adversarial machine learning. Adversarial machine learning is about learning in the presence of adversaries. And the attacks can happen at different stages of learning. It can happen at inference time, where adversarial examples can fool the learning system again, by perturbing the inputs to the learning system to cause the learning system to make the wrong decision. And they can also happen at the training time, where attacker can provide poisoned training data sets, for example, with the wrong labels and so on, to try to fool the learning system to learn the wrong model. Overall, adversarial machine learning is particularly important for security-critical systems. Due to the importance of this problem and this domain, numerous defenses have been proposed. In the last year and a half, there has been a couple years, there have been hundreds of papers posted on arXiv proposing different types of defenses. However, still today, we don't have sufficient defense that can provide effective defenses against the strong and adaptive attackers. And overall, I strongly believe that security will be one of the biggest challenges in deploying AI. And so far, we have looked at the one aspect of how attackers can attack AI, in particular by attacking the integrity of the learning system. The attacker can also try to attack the confidentiality of the learning system by trying to learn sensitive information about individuals. So now let me give you some examples to illustrate how attackers can do this and what kind of techniques we can draw upon to defend against it. As we all know, data is the new oil. However, and also this big data is one of the main power for driving the progress in deep learning. But however, a lot of this data is also very sensitive. And hence, handling the sensitive data can pose a lot of challenges. In particular, given time limit, I'll skip these. So in particular, one question is, as we train machine learning models, can these machine learning models actually leak sensitive information about the original training data? So this is one of the questions that we set out to explore in a recent work in collaboration with the researchers from Google. In particular, in this work, we looked at, do neural networks remember training data? And if yes, can attackers exploit this to extract secrets in the training data from just simply querying the learned models? So in this work, we in particular studied the domain of training language models. So in this case, we can take an email data set and try to train a language model. So a language model is when given a sequence of characters or words, and we'll try to predict the next character or the next word. So the question is, if we train a language model from, for example, a set of emails, then can an attacker actually exploit the fact that the trained model may remember information from the training data sets? Can it actually try to extract sensitive information from the original training data sets? For example, whether the attacker can, by just querying the model with a sequence of characters or words, to try to then steal sensitive information from the original training data set. So this is exactly what we did in our recent case study. In our case study, we trained a language model using an email data set called the Enron email data set. And in the Enron email data set, it's naturally contained users' credit card and social security numbers. Our work showed that an attacker, by just simply querying this trained language model, and by devising new attacks, attacker can actually extract the original social security and credit card numbers that were embedded in the original training data sets. This is an example demonstrating why, as we train machine learning models, we need to be very careful with protecting users' sensitive information. And in our work, we also propose a new metric called exposure to measure the degree of memorization. And our work has been used in Google Smart Compose to try to address this issue. So the good news here is that actually we, in this particular case, for this particular problem, we actually have a good solution. The solution is that instead of training just a vanilla language model, if we train a differentially private language model instead, then on one hand, we can still maintain utility of the language model. And on the other hand, we can significantly enhance the privacy protection for users' data. And the earlier attacks are no longer effective. So what is differential privacy? Differential privacy is a formal notion of privacy. And it essentially shows that when you have two neighboring data sets, where one data set has just one data point that's different from the other, in this case, one has one data point Joe's data more than the other data sets. And then in this case, if we compute a randomized function over these two neighboring data sets, and if the probability distribution of the results are close, then we say that this randomized function is differentially private. At a high level, essentially, it illustrates that an attacker, from looking at the results, simply won't even be able to tell whether Joe's data was used in the computation or not, and hence the computation result protects Joe's data privacy. So in our recent work, we also have been developing methods to enable automatic rewriting of data analytics and machine learning pipelines to ensure to provide automatic data differential privacy guarantees to ensure that the data analytics and the machine learning pipeline satisfies certain privacy policies, such as differential privacy. And some of our work has been deployed at Uber for protecting real-world analytics, and has been processing queries for like 500,000 queries per day. So given the time limits, I won't be able to go over some of the other parts of the talk. So in this talk, I talk about the two directions for the work at the intersection between AI and security. On one hand, AI can enable new security capabilities. And on the other hand, security can enable better AI. Security can help provide stronger integrity of the AI machine learning systems to help them produce intended and correct results and be resilient against attacks. And also, security can help provide stronger confidentiality and privacy protection for the learning system to not to leak user-sensitive information. And also another important aspect that I didn't have time to talk about is that we also need to develop techniques to prevent misuse of AI. Overall, there are many exciting and important open questions and challenges at the intersection between AI and security. For example, how can we better understand what security means for AI and the learning systems? How to detect when a learning system has been fooled or compromised? How to build more resilient learning systems with stronger guarantees? And how to build privacy-preserving learning systems? And how to democratize AI. So the work is in collaboration with many of my great students and colleagues and collaborators and so on. So overall, I strongly believe that security will be one of the biggest challenges in deploying AI. It requires a community effort. Let's tackle the big challenges together. Thank you.
Thank you, Dawn, for that great talk. We have time for maybe one question, and then we should break, given that we're a little over schedule. Go ahead, sir.
So is there any difference for adversarial example if you are dealing with a GAN, with a discriminator, or with just typical, typical network that with not using GAN?
Oh, okay. So the adversarial example is different from GAN, even though I think there's some words, common words in these two. So adversarial examples particularly is about by just adding specifically crafted perturbations to, for example, an image, and or to the input to the learning system that causes the learning system to give a wrong prediction, for example. And actually, in some of our recent work, we have shown that by utilizing GAN, we can actually automatically generate adversarial examples that have very different characteristics than the adversarial examples that are generated using other methods. Thank you.
Let's thank Don one more time.